So what is the value of I to the power of I, where I is the imaginary number I? Well, it turns out that the value of I to the power of I is a real number, and we're going to go over how to evaluate this expression. So we're going to be using Euler's formula to evaluate this, and I've already made a video proving Euler's formula. So I'll link the video in the description if you need a refresher, but I'll just use it without proving it. What we're going to do is rewrite the I in the base of the expression in exponential form, which is the form r times e to the power of I theta, where theta is a constant. Before we do that, we should first go over how to write I in exponential form. So let's suppose we have the complex number z equals I, which is the number we're working with. This is equal to 0 plus 1 times I, if we're considering the coefficients for its real and imaginary parts. So in rectangular form, which is the form z equals a plus bi, a is equal to 0, and b is equal to 1 in this case. What we need to do now is convert this into polar form, which is required before we can rewrite z in exponential form, which is our end goal. In order to convert into polar form, we need to work out r, which is the absolute value of the complex number z, and theta, which is the argument of z, or the angle between the positive real axis and the line going through both z and the origin in the counterclockwise direction. So to work out the values of r and theta, we need to use the formulas we have listed on the right-hand side. So for r, that's just equal to the absolute value of z, which is equal to the square root of a squared plus b squared. And we know that a is equal to 0 and b is equal to 1 in our case. So this is just equal to the square root of 0 squared plus 1 squared, which is just equal to 1. To find theta, we can use this formula listed at the side, and theta is equal to the argument of z, and we have all of these cases where we can determine the value of theta in terms of a and b. But the only one that's relevant to us is this one right over here, where argument of z is equal to pi over 2 when a is equal to 0 and b is greater than 0, which is the case that we have. So with the values of a equals 0 and b equals 1, we know that theta is equal to pi over 2. The value of theta can technically be pi over 2 plus any integer multiple of 2 pi. So theta could equal pi over 2 plus 2 pi k for any integer k. But we'll just assume the principal argument of I, which is pi over 2. So given that r equals 1 and theta equals pi over 2, we can rewrite our complex number z in polar form. So polar form is z equals r multiplied by cosine of theta plus I sine of theta, all in parentheses. So in our case, z is equal to r, which is equal to 1, and then times cosine of theta, which is cosine of pi over 2, plus I sine of theta, which is also pi over 2. So now we can rewrite this in exponential form using Euler's formula. So Euler's formula is e to the power of I theta is equal to cosine of theta plus I sine of theta. Well, that's the form we have here. We have cosine of pi over 2 plus I sine of pi over 2 in the parentheses. So this is just equal to e to the power of I times pi over 2, since theta is just equal to pi over 2. So this entire expression is just equal to 1 times e to the power of I times pi over 2. And we can get rid of this 1, since 1 times anything is just equal to itself. So this expression is just equal to e to the power of I pi over 2. So we can rewrite the complex number I as e to the power of I times pi over 2, which is its equivalent exponential form, and we're going to use this to evaluate the expression I to the power of I. If we look at the point z equals I plotted on the complex plane, we can intuitively see that the absolute value of z is equal to 1, since the line going from the point I to the origin clearly has a length of 1. We can also see that the line makes a right angle with the positive real axis, since the point lies on the imaginary axis, so theta is equal to 90 degrees, or pi over 2. It's fairly easy to work this out with a diagram, but what we did was the more rigorous proof. Alright, so now that we know that I is equal to e to the power of I pi over 2, we can substitute that for the I in the base. So this expression becomes e to the power of I pi over 2, all raised to the power of I. Using exponent laws, we can rewrite this as e to the power of I pi over 2 times I, which is just equal to e to the power of negative pi over 2, since I times I is equal to negative 1. We can clearly see that we now have an expression where both the base and the exponent are real numbers, which means the entire number must also be real. If we evaluate this number, it's approximately equal to 0.0279. If we had assumed that the value of theta was pi over 2 plus 2 pi k for any integer k instead of the principal argument, then I to the power of I would have been equal to e to the power of I times pi over 2 plus 2 pi k, all raised to the power of I, and this is equal to e to the power of negative pi over 2 plus 2 pi k. In this case, the exponent is still clearly a real number, so no matter which integer value of k we choose, I to the power of I is still a real number in any case. The reason why we ended up with a real number is because when we rewrite I in exponential form, there turned out to be an I in the exponent, since the argument wasn't 0, which would have occurred if it was a real number. Since this was in turn being raised to the power of I, the multiplication of I with I in the exponent with base e resulted in the real number negative 1. Since the exponent was a real number with the base of e, the entire expression was also a real number. This is also true for the general case, except the exponent would be negative 1 multiplied by some real constant, negative pi over 2 plus 2 pi k.